So in terms of this CFA playlist, we are still in the early quantitative methods or the foundations of quantitative methods. In the previous video, I reviewed some basic statistical concepts, and now I follow that up with a review of some basic or foundational probability concepts, including we want to hit these 4 topics in this video, starting with definitions. We want to get off on the right foot in terms of defining our concepts, including the distinction between an event and an outcome. And also we want to formally define what it means to be a probability, so that when we refer to a random variable, we have properly characterized that random variable with a probability or a probability distribution, and there are criteria for that. Then we have some important definitions in these 2 items here: conditional versus unconditional probability, and also joint probability. And then I'll show you my favorite way to wrap these all together. I didn't invent it, but I think the best way to look at it is with a probability matrix, where we have inside the cells of that probability matrix, we have joint probabilities, and outside we're going to have unconditional, aka marginal probabilities, and that will allow us, if specified, to really retrieve any of these probabilities: conditional, unconditional, and joint. And then finally, given that we can now define and characterize the random variable with its different properties, we'll look at calculating the expected value, which is the probability weighted average, and also the standard deviation of the random variable, which is the square root of its variance. So I look forward to going over these concepts. Let's start with 3 definitions. It's easy to gloss over these definitions and take them for granted, but it turns out that they do matter. First, let's consider the difference between an event and an outcome. You'll notice we define an event as a set of outcomes. At first, that sounds like, okay, what's the difference between them? Well, to illustrate, I have a single 6-sided die, so that would characterize a random variable, or we'd treat it as a random variable. And if we roll this 6-sided die, it would have 6 outcomes. We'll assume it's a fair die. And the 6 outcomes are 1, 2, 3, 4, 5, or 6. So we roll this die and can have 6 different outcomes. And an event is a set of outcomes. So we could define this and say, what is the probability that our random variable x, is represented by this die, is less than or equal to 3? And now that is the event that is defined by a set of outcomes that would be a 1 or a 2 or a 3. Similarly, if we wanted to define this as a probability distribution, we would want to include the other event that is mutually exclusive to this, and that would be the probability that x is, let's say, greater than 3. That is also an event that includes 3 outcomes, 4, 5, or 6. So you'll notice now I have 6 outcomes, but I've defined it in such a way that there are 2 events. One event is that I roll a 3 or less, that is to say a 1, 2, or 3, and the other event is that I roll a 4, 5, or 6. These 2 events are mutually exclusive, right? If I get an event that includes an outcome of 1, 2, or 3, it can't be this event, and vice versa. So these are mutually exclusive events. And also notice these are exhaustive, because I only have 6 outcomes here, and every time I roll this die, I'm going to get one of these 2 events. And so you can see we have these concepts: mutually exclusive events means an event can only one event can occur at a time. In other words, we can't simultaneously get both less than 3 and less than or equal to 3 and greater than 3. But also, these are exhaustive events. Every time I roll the die, I'm going to get one of these events. So sometimes you see this phrase, I see this in consulting a lot when we're itemizing possible outcomes. We'd say, are they mutually exclusive and cumulatively exhaustive? MECE, mutually exclusive, cumulatively exhaustive, have we included all the events? So you'll notice the die here, the outcomes, we can all agree on what the outcomes will be, 1, 2, 3, 4, 5, or 6, but we could define many different types of events. And one of these events could simply be 4, 5, 6, the probability that x equals 1. So we could call that an elementary event. This is both an event and an outcome. So that's the difference between event and outcome. And then the next definition is important, and that's the definition of a probability. So the probability has a specific mathematical definition. I'm not showing you the definition here, but it really has, I'm not showing you the math, but the math and the definition has two aspects. And so a probability measures the chance that an event will occur, and the probability of the event must be between 0 and 1, right? That should be familiar. Whenever we say the probability that x is equal to some event, we know to expect here something that's between 0 and 1, or 0% and 100%. Part of the definition of a probability is that it needs to be within these bounds. After all, we would not say that the probability of an event is 125%. If I said that to you, I think we would all be stupefied. We can't really process that. This in itself would contradict the definition of a probability. Secondly, if we really do have a probability and a probability distribution, then the sum of probabilities of mutually exclusive and exhaustive events must be 1 or 100%. And this is why not all distributions, not all nearly distributions are not probability distributions. A probability distribution is a very specific type of distribution where if I do a density curve, for example, that's my pretty lame normal. This could be any sort of distribution, but if the area under this curve was greater than 100%, we wouldn't have a probability. But if this were a standard normal curve, let's say, the area under the curve would be 1 or 100%, such that cumulatively, the cumulative distribution function would converge to 1.0 or 100%, and it would satisfy the definition of a probability. So the sum of our mutually exclusive and exhaustive events in the distribution needs to be 1 or 100%. So that formalizes two aspects of the probability that are probably intuitive to us, but they do have mathematical rigor behind them that I'm not showing. So then in terms of probability estimation methods, there are basically three approaches. And the first is subjective probability, where the estimation is based on personal assessment without any use of particular data. And believe it or not, this is very common. So for example, just last week, I was reading a blog that summarized an expert survey where they basically compiled questionnaires sent out to experts and in order to determine what is the probability of nuclear war, obviously a catastrophic event. And it was interesting to me because they had managed to summarize these probabilities, low probabilities, but they were non-zero. And I was just curious about the methodology, and it was clearly an example of subjective probability. They went out and sampled experts in order to determine what that probability is. And so that means there wouldn't be a mathematical database behind it. They got different answers from each person. So a lot of subjectivity goes into that. And then if we look at not subjective, we could have objective approaches, and there would be basically two there, empirical or a priori or a priori probability. So empirical probability also, this is extremely common, especially if we take a sort of big data or data science approach. So for example, if we wanted to estimate the probability that, let's say, a AA rated bond would default. Well, one way to do that probability of default on that bond is to go back and look at a historical sample of those bonds and how often did they default, and that could give us an empirical estimate. And then a priori probability based on logical reasoning would be something like, okay, we're interested in a certain event, and the event could be, we could have an outcome of x sub 1, x sub 2, x sub 3, x sub 4, and so we say the probability of x sub 1 equals some frequency of its outcome divided by the total. So maybe x sub 1, we would logically expect that to happen maybe once out of a total of 100 times. And an example of that would be that six-sided die that we looked at before. We don't need to roll the six-sided die. We don't need to perform a simulation in order to logically infer that it has 6 sides, and the probability of rolling a 1 will be 1 in 6. We have the concept of odds, and this will be familiar if you've done any betting or sports betting or something like that. But if we have the probability of E represent here, the odds is expressed a little differently. So, for example, if the probability of an event is 1/9, right, that is 1 divided by 9. Mathematically, 1/9, we would get about 11.1%. So we'd say the probability of that event occurring is about 11.1%. But the odds of it occurring are a different way of expressing it. We would say probability of the event, 1/9, divided by 1 minus the probability of the event, which is 8/9. And so the odds of the event are 1 to 8. And the odds against would be 8/9 divided by 1/9, or 8 to 1. Okay, so then we'll now get a little more specific about probability terms, and these are really important. I can't tell you how important it is to get these definitions down, get an understanding of these in there when we actually go to apply probabilities in finance. It comes up all the time. So we have conditional versus unconditional. So an unconditional probability is the probability of occurrence of an event that is not dependent on the occurrence of other events. And we sometimes also call this marginal probability. And as opposed to a conditional probability, which is the probability of an occurrence of an event given that another event has occurred. And so here is the notation for that. So it's important to recognize this as a conditional probability. And now I will read it. And there's 2 ways to read it, or at least 2 ways. What is the probability of A given B, or I prefer, because it's explicit, the following: what is the probability of A conditional on B? See how this is a conditional probability? If we wanted an unconditional probability of A, we'd just say the probability of A. So the notation is important. Here we have a fundamental relationship. The conditional probability, the probability of A conditional on B, is equal to the joint probability of A and B divided by the unconditional probability of B. And we'll look at joint probability in just a moment. But of course, we want to be able to rearrange this as needed. So we can rearrange this. I'll just multiply each side by the unconditional probability of B and say that the probability of B multiplied the unconditional probability of B multiplied by the probability of A conditional on B is equal to the joint probability of A and B. And then just by the way, so I think I'm following here the CFA notation, but this joint probability of A and B could also be denoted, we could also A comma B. I would read that as joint probability. And then if we want to use set notation, we could have intersection. I would also read that as the joint probability of A and B, but this seems like a safe way to do it. So let's apply it. And here we have multiplication rule of probability. So I just showed you that really, right? Joint probability of A and B is equal to probability of A conditional on B multiplied by the unconditional, aka marginal probability of B. And notice we also have this probability, I suppose this would be a symmetry principle. The joint probability of AB is necessarily equal to the joint probability of BA. So here's just an example. If we have the unconditional probability of A is 50%, the unconditional probability of B is 70%, and if the probability of A given B or conditional on B is 60%, then the joint probability of AB is 42%. How did we get that? Well, we took the 60% as the probability of AB, A conditional on B. We know if we apply this rule, multiply that by the unconditional probability of B, which is 70%, then we need to get the joint probability of AB or BA is equal to 42%. And then just by the way, what is the probability of B conditional on A? I would ask you, is it 42%? No, not necessarily, right? Because this symmetry here doesn't apply to the conditional probability. What we know about the probability of B conditional on A is that it's the joint probability of BA divided by the unconditional probability of A. And let's see, we've got 42% divided by unconditional probability of 50%. And I don't even need my calculator, fortunately. Dividing by 50% is multiplying by 2. And so that should be 84%. And I'll also inserted here two important points. Here is the test of independence. If the joint probability of A and B is equal to the product or of their unconditional probabilities, that is, say, probability of A multiplied by probability of B, then they are independent. A necessary condition that goes both ways. And so this is the test of independence. And what about that here? 42%, does that equal 50% multiplied by 70%, right? I'm just applying here the test of independence. I'm saying, does the joint probability equal the product of their unconditional or marginal probabilities? Well, 50 times 70%, that is 35%. It does not equal. And what I've done here is proved that they are not independent, right? We have independence as an affirmative test, fails the independence test, therefore, these are dependent. And actually didn't need to go to that trouble because I can just observe here, right, that if they were independent, it also follows that by the same math, that the probability of A conditional on B would be equal to the unconditional probability of A. And so you can see this 50 and 60% here does not equal to 50%. So I had a quicker route to understanding that they're actually dependent, not independent. And then here, secondly, if the joint probability is 0, well, that satisfies the definition of mutually exclusive events. For the addition rule, the probability that either of two events occur or both occur, you can see here the probability of A or B equals the probability of A plus the probability of B minus their joint probability. And so you will see this oftentimes conveyed with Venn diagram. So if we have the probability of A given here and the probability of B given here, then what we're doing is we're adding A and adding B, but that double counts what they have jointly in common here. So we subtract one of the double counting, and that gives us the total area. So here, for example, if the unconditional probability of A is 70% and the unconditional probability of B is 40%, and their joint probability is 35%, then the probability of A or B, right, is equal to 70%. And although not to scale, you can think of that here as 70% plus 40%. You can think of that here. And if we just imagine adding those together, we've double counted what's in here, their intersection. So we subtract one of them, minus 35%, and that gives us the total sample space here of 75%. Yeah, 70 plus 40, 110, minus 35% is 75%. So that looks correct to me. And that's a good thing we subtracted, right? Because if we just stopped at the 110%, we would know right away we haven't satisfied the definition of a probability. So independence and dependence, I already made reference to this. Independent events, occurrence of one event does not affect the occurrence of the others. And so we said if the events are independent, if A is independent, that means that the conditional probability of A, that is, say, the probability of A conditional on B, if A is independent of B, then that would necessarily equal the unconditional probability of A. Although here, again, is the key definition. This isn't just a criteria. We can use this as the test of independence. If they are independent if and only if, it's actually an if and only if. Well, let me put that another way. We could say if and only if independent, like that. So that's the test. If their joint probability is equal to the product of their unconditional or marginal probabilities. And then these two definitions are mutually exclusive, right? So it's an affirmative test of independence. If they either are independent, if they don't meet this criteria here, then they are dependent. So dependent is a broad umbrella of non-independent events. By the way, including, right, dependence would include correlation. However, the way that we typically define that's linear correlation. So linear correlation doesn't apply dependence because there are nonlinear correlations. So dependence is a broader set. But if these variables are correlated, then they are dependent, and therefore they are not independent. And so then we have total probability rule. The rule helps to explain the unconditional probability of the event in terms of probabilities conditional on the scenario. So if there are two scenarios, we could say S and then not S. And the not S is denoted here as S complement. So you would also see S with an apostrophe there to be not S. So you notice that's a convenient notation because these are mutually exclusive and cumulatively exhaustive. So just symbolically, if we consider the event of S plus the event that's not S, together we've included all possible events for S, and we really have a probability distribution of probability space. But then we say here the probability of A could be expressed as the joint probability of A jointly with S, plus the probability of A jointly with not S, or the complement of S. And then each of those, right, this probability, joint probability of A of S, as the joint probability of A and S, as previously discussed, we can express that as the unconditional, aka marginal probability of S, multiplied by the probability of A conditional on S. So we've expanded now the unconditional, aka marginal probability of A, here as a summation of these terms. And that can go on for more than 2 scenarios. Okay, so that's pretty symbolic, but what I did here is just try to represent it in the probability of matrix because, so I don't think this is exactly in the syllabus, the CFA syllabus, but it is in the FRM syllabus, and I think this is just a very superior way to solve problems and understand problems when we actually need to apply some of this, and that's with the probability matrix. And I've illustrated this here for the probabilities that we previously showed. And those were specifically, let me just capture the assumptions. I have to reference them myself. We were given the unconditional probability of A as 50%, the unconditional probability of B as 70%, and we were also given the probability of A conditional on B is equal to 60%. So given those 3 assumptions only, I'm able to construct here a probability matrix. And this is just such a great way to look at it. What we have here is A and then the complement of A and B and the complement of B. And so that inside the matrix we have joint probabilities, 1, 2, 3, 4, 2 times 2. The sum of the joint probabilities equal 100%, and then outside here we have unconditional probabilities. So let's just take the 3 assumptions that I'm given. Here we have probability, unconditional probability of B equals 70%. So that's this assumption right here that I hardwired that because we're given that. And you'll notice it's outside the cell. That's the unconditional probability of B happening. So if we take this, we would go down here outside the cell and find it to be 70%. We're also told that the unconditional probability of A is 50%. So that's a matter of, here's A, and going over to here, finding this unconditional probability outside the matrix, it's 50%. So similarly, this is also, I started by inputting this as a hardwired assumption. And then we have the probability of A conditional on B is 60%. And so then I just employed here the fact that if I take the probability of unconditional probability of B, multiply it by the probability of A conditional on B, then I need to get the joint probability of A and B. Right, so that means the joint probability of A and B is found right here. So I'm solving for this cell here at 42%. It is equal to the 60% that I'm given multiplied by this 70%. So in other words, I'll just draw it here. Unconditional probability is 70% multiplied by probability of A conditional on B is 60% because we're given that. And this is 42%. So I previously did show this math. And that gives me this cell here. So the 3 assumptions that I'm given allow me to populate immediately as sort of a first step these 3 values. And then it's just a matter of logical deduction. So if I take a look at the probability of B, that's this column here. Well, going back to the previous slide that I showed you, we know that if we take this joint probability and add it to this joint probability, which is after all the joint probability of B and the complement of A, adding those together in this column needs to give us the unconditional probability of B. So it's important at this point to understand the terminology that we're looking at a joint probability plus a joint probability here equals this unconditional, aka marginal probability of B. So you can see then I'm able to solve for the 28% because it's simply the difference between the 70 and the 42%. If you like, one way to think about that is that, or remember these, is that this 70% is, I prefer unconditional probability, but remember we said it's also a marginal probability, and it's in the margin. So that's a way to think about this. The 70% is in the margin. It's not in the matrix. It's a marginal probability. So we were able to deduce here this joint probability. And similarly, we can come over here and say, well, this joint plus this joint must equal this marginal probability. So that's the 8% difference. Similar here, the 22%. And now we have fully specified the probability matrix. And now we can really handle any sort of calculation, any sort of conditional probability once we've done that. And so let's look at an application here. A company is considering launching a new project. The probability that the share price will increase, given that the company launches the new product, is 60%. Oh, the probability that the share price increases if the company does not launch the project is 35%. If the probability of launching the new project is 70%, looks like I should have a comma there, what is the probability that the share price will increase? So here, this captures the assumptions, where S is the launch of the new project. So here is the probability that the share price will increase. Conditional on a new project launch is 60%. Here's the probability share price will increase. Conditional on not launching the new project is only 35%. And then here we have the unconditional probability of launching the project is 70% as opposed to its complement of 30%. And then so the question is, what is the unconditional probability that the company's share price increases? And the answer of 52.5% just applies, right, our total probability rule. We need to just account for the total probability space here. We could start here with the probability that the company launches a new project, 70%, right? That's probability of S, multiplied by probability of share price given the project launch of 60%, because this here gives us the joint probability of A and S, but we then need to add the probability, the complement multiplied by probability of the share price if we don't launch the project, the complement here. And so that is 30% multiplied by 35%, because that is giving us the joint probability of A and its complement S. And if we add those together, we're going to get the probability of A, which here symbolically is the probability that share price increases. So looks like 42% here, plus here, that's 42.0, sorry, 42.0%, plus here looks like 10.5% equals my 52.5%. Okay, and then I still think it's helpful to fit that into the probability matrix here, where now I'm saying here we have new product. Do we have a new do we launch a new product versus do we not? And over here we have share price increase versus not a share price increase. And so in terms of our assumptions here, I just started here with the 70% because that's this. The probability of launching the new project unconditionally or marginally is 70%. And then if I want to fill in this cell here, the joint probability of a new product and a share price increase, right, I would take the probability the share price will, this conditional probability of 60% multiply it by this 70%, and I'd get a 42% here, Well, that means I have a 28% here. And then I also note, since these two are cumulatively exhaustive here, I also know I have a 30% here. And up here I have 35% multiplied by the 30%, or 10.5%, meaning I'm left with 19.5% here. And then going across here, adding these two joint probabilities gives me an unconditional or marginal probability of 52.5%. Adding these two gives me marginal probability 47.5%. So that's the probability matrix that captures the scenarios. And then we just have the expected value. So the expected value is the probability weighted average of the possible outcomes of a random variable. Extremely common, right? The expected value of x is equal to the probability of x sub 1 multiplied by its value plus the probability of x sub 2 multiplied by its value, and so on. So extremely simple example here. Let's say for a company that we have 4 possible, what would I call these? I would call these events. 4 different events of $1.45, $2.30, $2.90, and $2.45 on the EPS, and then I would assign a probability to them. And what's the test here that we have a probability? Well, these need to be, again, mutually exclusive, cumulatively exhaustive, right? So each of these values needs to be between 0 and 1 or 100% inclusive, right? Which we do have that. These are recognizable as probabilities, but also they need to sum to 100%, 50, 100. So we do have that, right? If this column summed to 1.5, we would have something wrong. But now, given that, we can say, so we have a probability for each of the EPS outcomes, then we can say, what's the expected EPS? Well, it's straightforward application of this, right? It's 20% multiplied, I'm going to use the dot operator here, 20% multiplied by the 145, so I'll just put that in parentheses. I add that to 30% multiplied by 230, add that to 25% multiplied by 290, add that to 25% multiplied by 245, and you should get 232 as the weighted average or expected value. So you will notice that expected value means for us probability weighted average. Then the variance here is the probability weighted average of squared deviations from the random variable's expected value. So how are we calculating that? Expected here, you could see it's an expectation of the squared deviation. So here I have the outcome of $1.45, but now I would subtract here the expected value of x, that's 232. So that's my deviation in the parentheses, and then I'm squaring that and multiplying it by its probability. So 20% multiplied by here, the deviation squared, and I'm adding that to 30% multiplied by here, $2.30 as the outcome, and its deviation against the same expected value here squared plus 25% multiplied by 290 minus 232 squared plus finally 245 minus 232 squared equals, right? So I'm adding together 4 terms here. Each term is the respective probability multiplied by here. What we have is a squared deviation. The outcome minus, in all cases, that same expected EPS of 232, but that deviation is squared. So here we have the squared deviations. 4 squared deviations, they are each weighted by their probability, gives us the variance. Another way to do this, actually my preferred way, let's see if I could do this, is if we take EPS squared, and I'll have to just look at it because I calculated this separately. If I square the EPS here, I'm going to get that's 145 squared, I get 210, 2.3 squared is 529. 2.9 squared is 841, and 2.45 squared is about 6, 0. So now I have x, and then I have x squared here. And then if I say, what's the expected value of x squared, I'm multiplying the 20% times the 210, right? So I say 20% of the 210 is 0.42. 30% of the 529 is 1.59. If I say 25% of the 841, I get 210. And 25% of the 6 is 150. If I add those together, I get 561 here. And what is that? Well, that is the expectation of x squared. Why did I do that? Because I have here a better, well, in my opinion, a more useful definition of the variance, and that is, it's right. I'm still defining the variance. It's the expectation of x squared minus the expectation of x squared. See the difference? So what I've done here, and again, I had to go calculate the x squared values, in this case the EPS squared, and then to get the expected EPS squared, I need to multiply them each by those probabilities. I get 561, and then I need to subtract the expectation of x itself. That's the probability weighted average, 232 squared, and I would get that variance, 0.24. So in many cases, I consider that. So this is mathematically equal to this. And in many cases, I find this an easier way to calculate the variance. Just depends on the situation. And then the standard deviation, having the variance is the hard part, but the variance, of course, those units are in squared units, so they're not intuitively useful. But if we take the square root of it, we get the standard deviation. So in this case, square root of the 0.24 is 0.49. And so why is the standard deviation so helpful? Well, I forgot these lines here, but these EPS are in dollars, right? $1.45, $2.30, $2.90. What's the variance? Well, it's dollar squared, 0.24, not immediately useful to us, or intuitive to us, I should say. But the standard deviation of 49, that's just in dollars. So we can now say the standard deviation of this EPS is 49 cents, right? Much more intuitive. And because it's just a square root, it's functionally equivalent, right? We can almost, in many cases, we can refer to the variance or the standard deviation because they are square and square root functions of each other, functionally equivalent, but much more intuitive to talk about standard deviation because we can immediately think about that as a measure of dispersion. And then almost done, if we take, we have a total probability of rule, the expected value of x in terms of conditional expected values. So that's symbolically here, but then let's just go right to the application. Total probability rule for expected value using an EPS example. So here's the assumption. What is the expected value of the EPS given that the probability of decline in interest rates is 30%? So I represented that here in green. So 30% probability of a decline in interest rates. If the interest rate declines, the chance that the EPS will increase to $2.50 is 60%. So let's just pause and ask ourselves, what is that 60% here? What kind of probability is that? That's a conditional probability, right? The probability that the EPS is $2.50 of 60% is conditional on a decline in the interest rates. We could say this 30% decline in interest rates is really an unconditional probability. And so if the EPS does not go to 250 in this binomial tree, then it has a 40% chance, on the other hand, of going to $2. On the other hand, if we go back to the unconditional here event, if the interest rate doesn't decline, it will increase with 70% probability. And then let's see here, if the interest rate increases, the probability that the EPS will be $1.50 is 50%, and the probability that the EPS will be $1.75 is 50%. So this is a 50 for 50, and these also are conditional probabilities. These are conditional probabilities, conditional on the event that the interest rate increases. And so we're solving here for the expected EPS. And the one way to do this is to take these EPS, these two events here, 50% of $1.50 and 50% of $1.75. That means here that the expected EPS, if we were up here in this event, is the weighted average, right? 50% times $1.50 plus 50% times the 175, or really the average, is $1.63. So the expected EPS in the event of an increase in the interest rates is $1.63. Similarly, we can come down here and say 60% times $2.50, $2.50 plus 40% times $2 is equal to $2.30. So here we have the EPS in the event of a decline of interest rates. And then taking another step back here, we can get to the 183 by, again, applying that same sort of backward induction, 70% multiplied by 163. Or let me just explicate here, 70% multiplied by 163 plus 30% multiplied by 230 equals our $1.83. So we apply the total probability rule to get the expected value of the EPS given the set of probabilities. So we'd get the same answer if we came out here, and we'll notice that here, right, we have unconditional. The interest rates can either go increase or decrease. And then conditional on that event, we have these conditional probabilities. But that means we also have joint probabilities here, right? So what is we have four outcomes here. What is the joint probability of this outcome? Well, it's the unconditional 70% multiplied by the conditional 50%. It gives us a joint probability here of 35%. And here, similarly, we have a joint probability of 35%. And here we have, let's see, 250 times, 30% times 60% is 18% jointly. And then my 30% times 40% here is jointly 12%. And these are joint probabilities for the four outcomes. So just as a test here, they should add to 100%, 35, 70, 88 plus 12, 100%. We do have a valid probability distribution here. And then we can say $1.50. Well, let me get rid of my arrows here. Let me just express the joint probabilities. 35, 35, 18, and 12. And then I'm just going to multiply $1.50 times the joint probability. And it looks like I get 0.53, 0.61, 0.45, and 0.24. So if I add those all together, I get the same 183. Another way to get there. Okay, great. Then finally, properties of expected value. Expected value of constant times a random variable equals the constant times the expected value of the random variable. So you could just see here notationally that the weight, this is typical portfolio notation. We have weights applied to returns, but the weight here is denoted with a small w, and it's a constant in the weight, so it comes out. And so it's equal to the weight multiplied by the expected value. And then the expected value of the weighted sum of random variables equals the weighted sum of the expected values with the same weights. So here we've just distributed this out and sort of extracted the constant weights out from their parenthetical expressions. And so that is a review of the probability concepts. I hope that's helpful. Please subscribe to the channel. If it is helpful, subscribe to the channel, and then you'll get notified of the next video in my series on this CFA playlist. Thank you.